Chapter 12 is going to start dealing with physics. We did the first half of the year we were doing chemistry, which is the interaction of matter and how they combine or repel or just blend with each other. Well, we're done with that now. It's over. We're moving into physics, which is the motion of matter. So how matter moves. So the first thing we have for the notes is called frame of reference. You just saw a short video on that and answer some questions. So the object or point from which movement is determined is the frame of reference. So from the short video you saw that wherever you were standing, whether it be the car, the ground, or the plane, things appeared to move different. Of course, again, from that same video, the most common frame of reference is the Earth. Everything we see is happening because the Earth is what we're on. Whether in your house or your car or even on a plane, the Earth's still there and it's big. And we recognize it, we identify it. So everything seems to move with the Earth. And don't be confused, because the Earth is not always the best point of view depending on where you're at. Now, another way to look at point of reference in case you're still struggling, you have these four boxes and a yellow ball. And you look at that and say, well, the yellow ball's in the middle and the box is moving up as we go from left to right. Or it's possible the ball is dropping within the boxes. But again, it depends on if you're focusing on the ball or the box. And there's no wrong answer. It's really wherever you choose to be the point of reference or the frame of reference. Movement can be measured only with reference to something that is assumed to be fixed in place, again, like the Earth. Or you're standing on the side of the street watching the cars go by. Or you're in the car watching the people go by. Walking down past a building. Rolling on a skateboard, watching things go by, or while you're on a skateboard, the skateboard seems still and the building's going by. Pencils are still, bullets moving. But something is consumed to be stationary, something else is moving. Again, we all know you're in a car and you're moving along the Earth, and your distance is moving from one spot to the next, moving down the road. Well, as I said earlier, the Earth moves around the sun. And we see that every day that's the rotation, but we see that as the Earth goes around the sun once a year, changes our climate and our weather accordingly. But hey, even our suns and other stars move, and if you look towards the northern star, which is located right inside of that circle there, all the other stars seem to rotate around that. Well, that's only because they're not moving. What's happening is our Earth is spinning around, and the center point appears to be the northern star right in the center. Hey, even our sun's in a galaxy. And the galaxy seems to be still compared to other things out in the universe, other galaxies. And even in the entire universe, it can be a small item. And nothing seems to be moving at all in the universe. All right, moving on to section 2, speed and velocity. Motion is a change in position relative to a frame of reference. So you started here and you moved along here. The frame of reference is still where you started, and you moved from part A all the way up to part B. And it took some measure of time to get there. That's our speed. Motion is measured in distance and time. How much distance you cover and how much time does it take to do that. That dictates the speed. Speed is the distance traveled by a moving object per unit time. So it's distance divided by time. Shorter way, we're going to be using these formulas pretty soon. S equals distance divided by time. S equals d divided by t. Now using algebra, we're going to rearrange these three variables to find the other two. So I can multiply both sides by t. Okay, so times t and times t, and then I'll get d equals st. Well, I could also find t by dividing both sides by s. So t equals distance divided by speed. So we can find all three variables, speed, time, and distance. And we will do so shortly. Skipping the video for now, we don't need to do these. Give me a second. All right, constant speed. Its speed does not change. Cover the same amount of distance over the same amount of time, nothing changes. It moves along. An object at rest is constant speed. Zero. Zero is still a speed. It's a number. You're going nowhere, and you're constant. Constant speed is always going to be a straight line. So this graph shows it pretty well. You're moving, let's see, what is it, 100 meters distance over 2 seconds of time. 100 meters, 2 seconds. 100 meters again, 2 seconds, and so forth and so on. Gives you a straight line. That's constant speed. The slope is directly related to the speed. So the red line, again, is the constant velocity, constant speed. You have these points, and they have, an x and y value, x2, y2, okay? And, you can find the slope, if you remember your slope formulas. And the slope is going to be that speed. It's the change in the y. How much you've gone up, distance, how much time it took you. Distance divided by time. The y is divided by the x. The steeper the line, the faster the speed. So the lines on this end going like up steeper here, they have more rise and less run, higher slope, more speed. Lines over here have smaller rise, a longer run, they are slower. Of course, less steep the line, the slower speed, as I just said. Our average speed. Speed of a moving object is not always constant. In this graph that we have, now this is velocity versus time. Velocity here at zero velocity. And as time up to 2 seconds here, it's going up to 3 meters per second. Then at that time between 2 and 5, in this area in here, between 2 and 5, the speed is constant, isn't it? It's staying at 3. It's still at 3 at 2 seconds. It's still at 3 at 5 seconds. But don't you know, later on, it starts going from 3 seconds all the way down here to 0 again over the last 3 seconds. And we can use a method here shortly to show you how to get average speed. The formula for this is total distance divided by total time. So here's kind of a weird question. What's the average speed after 4 seconds? Well, at 4 seconds, you're here. Okay, you didn't go anywhere. At 2 seconds, you're far away, but then you backed up. So you've gone a total distance here. At 4 seconds, you've gone 0 meters. Over 4 seconds, that's still zero. That's zero average speed. Even though you ended up at this part right here, you didn't go anywhere. You went back. Later on in the graph, of course, you're ending up here at between 12 and 14. But even then, you start going backwards down to this point. The average speed for the entire graph here would be, I'd say it's about 7 meters divided by 10 seconds. That's your average speed. Right here, this whole point here, I'm circling and circling. That is total distance and total time. All right, velocity, a new term, but it's exactly the same as speed. Velocity is the speed in a given direction. You can go east, go west, north, south, but it has a clear and distinct direction. Usually they're in degrees, on the 360 degrees in a circle, but a little complex for what we need to do. Here's an example, 20 kilometers per hour east, represented by arrows. So there it is, 20 to the right. Now the head, that's this part, tells you which direction it's going. And the east is to the right. The tail gives you speed, so the longer the tail, the more speed there is. Again, this is 20. The longer the tail, the faster. The shorter the tail, the slower. So this one here, let's say this could be 20. This one could be 5. This is scaling. Okay, not very important here for now. Just recognize the length is the speed. Now velocity in the same direction they can add. Let's say you're going 10 miles an hour. If you're on a bus going 10 miles an hour, and you walk forward on that bus at 10 miles an hour, your actual speed, you the person, not the bus, you the person is going 20 miles per hour. That's kind of odd, right? Let's say they can also subtract in the opposite direction. So the bus again is going 10 miles an hour, and now you're walking to the back of the bus at 5 miles an hour. Well, your actual speed then is only going to be 5 miles per hour. It will subtract. Velocities at angles add trigonometrically. So, if you're going, say, 10 this way and then 10 down, you'll get some resultant vector, they call it. That'd probably be around 12. It doesn't, if you're a sailor, you're aware of these terms when you're out on the water. But they don't add directly. You have to do a little math, and again, that's going to be above and beyond what we're going to do in this class. All right, next you have some worksheets to work on, working with speed, constant speed. Good luck.